So, first part of chapter 9, we talked about molecular orbital theory. And remember, we're only doing first and second row diatomic molecules with that. It can be applied to any molecule. That's all we talk about here. And then the second theory of bonding or structure in this chapter is called hybridization theory. It's a totally separate theory. It's neither better nor worse than molecular orbital theory. Sometimes one's the appropriate one to use, sometimes the other is, right? And it just depends upon, what does the job at hand better. This is a quick way, the way, for you guys to figure out what the hybridization of the central atom is in a molecule. And in this class, we're only going to hybridize the central atom. We're not going to hybridize any of the peripheral atoms. What we're talking about here, for the most part, now I'm going to do a bunch of examples today, are, for the most part, it's one central atom, the rest are peripheral atoms. I'll show you what you do when there's, like, say, a chain of carbon atoms. We'll do that too, but it's the same idea. And this relates directly back to Vesper theory, valence shell electron pair repulsion theory. Remember, that was when we were trying to figure out the electron group geometry and the molecular geometry. You guys remember that? And one of the things that you need to do to figure out what the geometry of a molecule was count up the number of electron groups on the central atom, right? And just to remind you, because this trips people up every now and then, an electron group is either a little pair of electrons or a bond. And remember, it doesn't matter if it's a single, double, or triple. That bond just counts as one electron group. Okay? So all you have to do to figure out what the hybridization of an atom is look at how many electron groups there are on it, and then go by this table. Right? sp, sp2, sp3, sp3d, sp3d2. This is pretty much all, pretty straightforward. If you need any help, the superscripts always add up to be equal to this number. Remember, if there's nothing there, that's an implied 1, right? 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, right? 3 plus 1 plus 1 is 5, and so on, right? See how that works? The number of hybrid orbitals that form is the same. So I didn't really see a table exactly like this in your textbook. There's a similar one on page 290. It just says number. It doesn't say number of electron groups. It says that. It basically gives this number and that, plus some examples and angles and stuff. Memorize this. 290. If I were writing that table on page 290, I would just include this column right here too. So do you guys remember last week when I was taught, I started with the example of methane, CH4, and I explained how we couldn't adequately describe the bonding in terms of plain atomic orbital overlap. Remember, because of the p orbitals, okay. And how they're 90 degrees to each other, and they wouldn't. And we know what we know experimentally about methane is that the bond angle of all 4 bond angles are all 109.5. About they're all the same as each other. All the bonds are the same, equal length and equal strength. So if you look in your notes, you'll see how I showed you that you can't get that with just pure valence orbitals, the p orbitals and the s orbitals overlapping. But when we hybridized on the carbon 2s and the 3 carbon 2p orbitals, mixed them all together and hybridized them. Do you remember that picture? It was this. And they have pictures in your textbook of what the hybridized orbitals look like. It's just a combination of an s orbital, which is a sphere, and 3p orbitals, which are those lobes, right? Have some p characters and this character too. Well, let's say we were trying to figure out hybridization of the carbons in a setting. Can you guys tell me what hybridization is? How did you get that?
Just SP.
SP, right. So all you do is come over to this table here, right? So I pointed to this carbon, so that's going to be our central atom, right? Say, how many electron groups are there on that carbon? And what's the answer?
2.
2, because remember, that triple bond counts as one group. Remember that?
Yeah.
Right. Don't want that fully. Okay. So we've got 2 electron groups. That means it's sp hybridized. That's it. It's easy as that. Okay.
Yeah, it's an S.
Definitely. What's the hybridization of that carbon right there?
SP2.
Good, that's it. See, that's all there is to it. 3 electron groups. 1, 2, 3. sp2. So we've been drawing Lewis structures up to this point and getting single, double, and triple bonds. Single bond is what we call a sigma bond, and I'm going to define sigma and pi for you in a second. Double bonds is sigma and 1 pi. Triple bond is a sigma and 2 pi's. So first of all, one thing is that anytime there's any bond at all, it's at least, covalent bond, there's at least, there's a sigma bond, there's one sigma bond. If it's beyond a single bond, double or triple, then the other bonds are pi bonds. Sigma bond is a head-on overlap of two orbitals. It could be any kind of orbital, sp,d, sp3, sp3d, a hybrid orbital, an unhybridized orbital, doesn't matter. If it's head-on overlap, then it's a sigma bond. The picture might look like this. Let's say a p orbital on this atom, doesn't matter what the atom is, and a p orbital on this atom are overlapping. They overlap like this. Right? You know, these orbitals are all 3D, right? So it's like that. But if they head on, if they overlap head on like this, it forms what we call a sigma bond. It ends up with a sigma bond. You get better overlap, more overlap of the orbitals. They overlap, you know, there's just more volume where they actually overlap. And what that means is that there's more electron density in a sigma bond than there is in a pi bond, everything else being equal. The more electron density there is, the stronger the bond. What a pi bond is sideways overlap of unhybridized p orbitals. That's the only type of pi bond we're ever going to deal with in this class. It has to be a p orbital on this atom and a p orbital on this atom, not hybridized. They overlap sideways. I'll draw the picture in a minute. They make a pi bond. It ends up in pi bonds. There's less overlap than a sigma bond, and so they're weaker than a sigma bond. So there's the atom right there. There's the nucleus. If you overlap like that, you get a pi bond. Going back to the example I did a minute ago, the ethylene. Can you guys read all that? It's the sideways, right? Sideways overlap, and it looks like this, right? A few minutes ago, you guys said correctly that the hybridization of each of these carbons is sp2. In terms of the atomic orbitals that combine to make sp2, carbon, you would take, there's one s and two p's. That's what the 2 means, is there's two of the p orbitals in there and one s orbital. So this one and any 2 of these make 3 sp2 orbitals. But this one 2p orbital, this p orbital that's not involved in the hybridization, it's still there. Right, orbitals are conserved, right? Count them, it's good. 1, 2, 3, 4. 1, 2, 3, 4. You guys following? And so, what that means is whenever an atom, whenever we think of it as being sp2 hybridized, we think of it as having 3 equivalent hybridized sp2 orbitals and 1 unhybridized 2p orbital. What's the molecular geometry about that carbon? I know I'm going back to a previous chapter, but you guys remember this? Trigonoplanar, good. And who said that? You're right. Right. How did you know how to do this trigonoplanar?
3 electron pairs.
Exactly, 3 electron groups, right? Yeah, you're right. Which means that it's 120-degree bond angle, approximately, each of these. Because the way that you can tell that an atom is sp2 hybridized is the number of electron groups on it, and the way that you tell what the least electron group geometry is the same thing, the number of electron groups on it. It's, one tells you the other. If an atom is sp2 hybridized, then at least its basic electron group geometry will be trigonoplanar. If it's sp3 hybridized, it'll be tetrahedral. If it's sp, it's going to be linear. You guys following all that? Just sp3d, that's 5, so that's going to be trigonal bipyramidal. There's sp3d2, that's 6, that's octahedral. Remember all this stuff? So, what we know about this is about this carbon, bond angle is about 120 degrees. sp2 hybridized, which means that on that central carbon, there are 3 sp2 orbitals. And because the geometry is trigonoplanar, those sp2 orbitals must be at a 120-degree bond angle from each other, right? So, an sp2 orbital, 2/3 p and 1/3 s, might be something like that. Right? That might be one of them. Another one would be something like that. The other one would be down here. The center is the carbon atom. Over here, there's a hydrogen. Well, hydrogen, remember, we don't hybridize peripheral atoms, but hydrogen you wouldn't anyway. There's just one electron, it's in a 1s orbital, right? 1s orbital is spherical. What overlaps like that? Same thing over here, say? I'll call it this one. And this one is connected to this carbon right here. This is a double bond. What kind of bonds make up a double bond? It's 1 sigma and 1 pi, right? So the sigma is head-on overlap. And that head-on overlap, I'm going to change this a little bit so I can draw it. It's going to be with the carbon over here. And that's sp2 orbital from it. There's 2 others. You see what I'm trying to draw? Gets kind of mixed up. But, yeah. What I have here is the sigma framework for this molecule. I have all the sigma bonds shown by the head-on overlap of these orbitals. On this carbon, there are 3 sigma bonds. 2 of them to hydrogens, right? That will be here and here. So this sigma bond and this sigma bond both formed by the head-on overlap of a hydrogen 1s orbital with a carbon sp2 orbital. Right? This and this both. This sigma bond here is formed by the head-on overlap of a carbon sp2 here with a carbon sp2 orbital on the other carbon. What we're doing is we're describing the bonding in this molecule in terms of hybridization theory and orbital overlap. It's one of the things that I'll ask you to do. This and this are the same, right? These are, you guys see these are both carbon sp2 with a hydrogen 1s sigma bonds. What do we have left?
Pi bond in the middle.
A pi bond, that's it really, right? Okay. What's a pi bond again, definition?
Sideways.
Of what? Unhybridized p orbitals. So, what that means is there's going to be a p orbital on this carbon and a p orbital on this carbon that are not hybridized and have to overlap sideways. Because the 3 sp2 orbitals are all in the plane, 120 degrees from each other, trigonal planar, the p orbital that's not hybridized is perpendicular to that plane. Can you guys picture that? And so we would have, in this picture, a p orbital sticking out of the board and going back into the board, and the same here. And they overlap sideways, like this. I drew them too far apart so it doesn't look like they would, but they're close enough together to where this p orbital and this p orbital would be overlapping sideways, forming the pi bond. See that? Try it out. sigma framework. So now just the pi part, instead of trying to put it right on there. So all that stuff's still there. But now I'm going to twist the molecule 90 degrees so that I can draw on the plane of the board. There's going to be a p orbital there, not hybridized. P orbital there. These are the ones that are, in this picture, will be coming out of the board and going back into the board. They overlap sideways, they form a pi bond. And it's formed by the sideways overlap of a carbon 2p with a carbon 2p. You guys got that? You know it's 2p and not 3p or something else because the valence electrons in carbon are 2s2, 2p2.
You said it's just a framework. Are the electrons free to move like throughout, or are they stuck in the bonds?
Well, we call it a sigma framework because it's like the skeleton. It's like that's the shape of the molecule, and the pi bonds, the electrons and the pi bonds, they're kind of on top of that. So, are the electrons free to move about? Well, somewhat, but that's more of a molecular orbital picture.
Oh, okay.
Right? When we're using hybridization theory, we still keep things localized. That's the way we have to look at it. So now we have a complete description of the bonding in ethylene using hybridization theory and molecular orbital, not molecular orbital, and orbital overlap. So it would be, so now that you guys have that picture, there are 4 equivalent carbon-hydrogen sigma bonds that are formed by the head-on overlap of a carbon sp2 with a hydrogen 1s. So 1, 2, 3, 4. There's also a carbon-carbon double bond, which has a sigma bond. Which is formed by the head-on overlap of carbon sp2 with carbon sp2. Sigma, carbon sp2, sigma, carbon sp2. And also pi bond. Which is a sideways overlap of the carbon 2p with the carbon 2p orbital. So, let's do the same thing for this one. So, our goal is to describe the bonding in terms of hybridization theory and orbital overlap. In other words, using hybridization theory, which orbitals are overlapping with which kinds of orbitals. So to do that, we need to know, first of all, the hybridization of the central atoms. And you guys already told me, just remember, what's the carbon?
SP.
SP, right? One from our SP. What that means is, for each carbon, the 2s orbital and one of the 2p orbitals mixed together to make 2 sp orbitals. But that leaves 2 of the 2p orbitals unhybridized. In sp hybridization, 2 electron groups, what's the bond angle going to be?
Linear?
The angle.
180. Oh, 180.
180, right? So 180, 180, right?
Yeah.
So let's describe this bond right here. It's a single bond, right? Which means it's a sigma bond. Which orbitals do you think overlap to form that sigma bond? Which one?
S.
S. Any particular one? 7s on a lead atom? You know.
1s, 2s.
2s. Which atom? Which atom has which the s orbital from which atom? You know, Devin? Hydrogen. And so it has to be 1s because it's ground state, right? What kind of orbital is it overlapping with on the carbon, do you think? Is there, okay. What happened to that 2s? It's not there anymore, right? It's mixed in with the P's, and so it made the hybrid orbitals.
So it's overlapping with the sp.
And it's P on the carbon. Let me draw that picture for you. That might be an sp orbital on the carbon. Because there's two electron groups, sp orbitals are 180 degrees from each other, like you already said. They're supposed to be the same as each other, but I drew them a little bit bigger. No. Anyway, there's the carbon atom. There's one sp orbital pointing this way, one sp orbital pointing this way. This one's overlapping, as you guys already told me, with the hydrogen 1s. And so this sigma bond is head-on overlap with a hydrogen 1s with a carbon sp.
What's the other SP bond?
Where's it going to? What's this carbon connected to besides hydrogen? The carbon. So the other carbon is just like this carbon. It has an sp this way, sp this way. So there's the sigma bond between the two carbons, right? hydrogen over here. There's a sigma bond. So we can say carbon-carbon bond's a triple bond, right? And we've already seen that whenever there's a triple bond, there's one sigma and two pi's, right? Remember that? Right up there? Which orbitals are overlapping to make the sigma bond between the two carbons? The what? I just didn't hear, that's all.
SP.
Yeah, two SPs. I think those are said, Brandon, I just didn't hear. No? They're the SPs, right? Just like I tried to draw in this picture here. This SP from this carbon with this SP from this carbon right here. There are two pi bonds. Which orbitals do you think overlap to form the pi bonds?
The remaining p orbitals.
The remaining unhybridized p orbitals on the carbons, right? So it's going to be a carbon 2p with a carbon 2p. One of these on this carbon, and this other carbon has the same thing, so it has a p orbital too. So this would look, there's two pi bonds. One of them would be in the plane. So on this carbon, we have 2p. On this carbon, we'd also have a 2p. Kind of see that? It overlaps sideways. Now that would be one of the pi bonds. Where do you think the other one is? Yeah, it's 90 degrees. Remember, p orbitals on the same atom are 90 degrees to each other. This one's straight up and down. The other one's going to come out of the board and go back into the board. So it'll be one here and one here, overlapping sideways. Getting that picture? So. Sigma pi bonds. Let's do one more molecule. So you can you see how a multiple choice question might be asked? Might say in this molecule right here, the one I just erased, acetylene. Which of the following describes the bond between the two carbons? And and it might be a carbon sp3 with a carbon 2p, some nonsense like that. But the answer would be a carbon sp2 with a carbon sp2, sigma carbon sp2 with sigma carbon sp2 plus 2 carbon 2p pi carbon 2p bond. Carbon 2p, carbon 2p. Are you guys catching the notation here? So that's the type of bond sigma. It's sort of a subscript. The subscript is the orbitals that are overlapping to form this bond. So it's a sigma bond between a carbon sp2 or whatever it is, right? Sp doesn't matter. It's the same notation. Carbon sp and a hydrogen 1s. See that?
just intriguing, right?
Yeah, it's the same one.
Just a little bit.
Yeah, it's actually that way. Yeah. And you know where you're going, the two peaks, right? Because that one's kind of confusing. See, what he does is, I don't even know what he says. It's like, forget that it's not. It has to be so usually it's like very to the point. Yeah. I don't know why there's 3 years.
Now you know enough to do the same thing for this molecule. That is, to describe the bonding in terms of hybridization theory and orbital overlap.
Should I use the third?
Yeah, that makes more sense.
So first, what?
Just like the whoa.
You haven't seen. First thing you're going to want to do is figure out what the hybridization is of each of the central atoms. The ones on the outside, there, and there, you don't have to worry about because you don't hybridize. We're going to want to know what orbitals are occupied, but we'll get there. So let's look at this one right here, this oxygen. You guys tell me what the hybridization of that oxygen is.
It's just
The smallest.
I'm doing a few different things.
Which oxygen?
The one on the far left.
Oh, for left.
What's that?
wait, you said the oxygen on top?
The carbon or oxygen?
I'm talking about this one right here. This one we don't have to worry about, it's a peripheral one.
Yeah, I was gonna say. So it's just SP, right?
Yeah.
Oh, electron groups. It's
Electron groups, how many electron groups are there?
Oh.
Is
yeah,
that SP3?
SP3.
It's a voice in the wilderness, as you guys know. Look back at your table that I gave you in the beginning of class today. Very left-hand column said number of electron groups. And remember from when we're doing Vesper theory that electron groups are either lone pairs or bonds. So there are 1, 2, 3, 4, 1, 2, 3, 4 electron groups. That makes it sp3. Tetrahedral, 109.5, all that stuff. Okay. What about this one?
Same thing.
Yeah, here in SP2, that's right.
Oh, the
This part right here.
SP3.
Yes. There are 1, 2, 3, 4 electron groups. It's sp3. Are you guys starting to see it?
Yeah.
And the nitrogen.
SP3.
sp3, right? 1, 2, 3, 4 electron groups. sp3.
Everything until this point.
Notice, right, that the only place there's any pi bonds is right here in this molecule. And the central atom is sp2. That means that there's one p orbital that's not hybridized. You need that because that's what a pi bond is. It's a sideways overlap of unhybridized p orbitals. Without that unhybridized p orbital, you couldn't make a pi bond. See it? So we're going to go through one by one each of these bonds. What we're doing is we're looking at each bond. That's bond, that's bond, that's bond, that's bond, and so on. And describe which orbitals are overlapping to make each of these bonds. That's what we're doing here. So one by one. First one, oxygen, hydrogen. What kind of bond is it, first of all? You know what, let me label them and then we'll make a list, right? So A is the bond between the hydrogen and the oxygen. What kind is it? What kind of bond?
Sigma.
Sigma bond. Which orbitals are overlapping to make that bond? Hydrogen. Hydrogen what?
1s.
Good. So hydrogen, 1s, and oxygen, I heard, what kind of orbitals overlap? sp3, right? It's the hybrid orbital. And that's it. No?
Yeah, I think.
Okay, I don't know if this helped, but remember that the definition of a pi bond is a sideways overlap of unhybridized p orbitals. What that means is when we're using hybridization theory like this, the sigma bonds are all, at least from the point of view of the central atom, sigma bonds are always going to involve the hybridized orbitals. So, you guys told me this is sp3, and so the sigma bonds are all, from the oxygen, it's always going to be the sp3 on that side of the sigma bond. What kind of bond is it?
Sigma.
It's a sigma, right? Because it's a single bond. Which orbitals overlap? Which one on the oxygen and which one on the carbon?
sp3.
Oxygen sp3. Good. I heard somebody said sp2, right? Carbon sp2. That's it, right? Okay, so far?
Yep.
C. Kind of bond.
1 sigma, 1 pi.
Good. There's two bonds, one sigma and one pi. What's the sigma? Which orbitals are overlapping? What's coming from the carbon?
Carbon sp3. Or
Carbon sp2, right? Now, we're not going to hybridize the oxygen, which means that the electrons are all in 2p or 2p or 2s orbitals, right? We're going to call that 2p. There's also a pi bond, right? Which orbitals are overlapping to make that pi bond? From the carbon, what kind of orbital?
P?
S.
No.
2s. 1.
2p.
Pi bonds are never hybrid orbitals. They're always unhybridized p orbitals. Remember that, always. It's straightforward, then there's no exceptions, you'll be happy to know, right? For us, right? A pi bond is always a p orbital and a p orbital, not hybridized. Sideways overlap. So the pi, carbon 2p with what on the oxygen? 2p. Oxygen 2p. And you know it's 2p, not 3p or something else, because you know the valence electrons in oxygen are 2s2, 2p4.
Where do the s orbitals in the oxygen go? Or do they not bond?
So oxygen looks like this. All right. So before we continue with the rest of the molecule, Josh brings up a good point. So we need to discuss this just a little. We'll come back and we'll look at this oxygen too. But let's do this one first. On the oxygen out here, okay? Oxygen's electron configuration, valence electron configuration is 2s2, 2p4. Favorite arrows again, right? Two lone pairs, right? That means two sets of electrons that are paired up with each other. There you go, lone pair and a lone pair. See that? No? A lone pair is two electrons that are in the same orbital, opposite spins, but they're in the same orbital, right? There's two electrons in the same orbital. There's two electrons in the same orbital. These are the lone pairs, so this is a lone. Lone pair, lone pair. The oxygen, remember we're talking about this, forms two bonds. It forms a sigma bond and a pi bond. It doesn't matter which is which. One of them forms a sigma, one of them forms a pi. So the geometry looks like this. You know that these orbitals are 90 degrees to each other? Kind of like that, right? If this is the sigma, then the pi is going to be sideways overlap this way. See that?
Yeah, makes sense.
Makes sense? Okay so far?
Mm-hmm.
Now this oxygen right here, see if you guys can figure this one out. We already said that this oxygen right here, it forms bond A and bond B. It forms a sigma with an sp3 onto the hydrogen, also forms a sigma with an sp3 over to the carbon, right? This is still the electron configuration for oxygen, right? When we hybridize it, sp3, we have the same number of electrons. So now on this oxygen, we hybridize it because it's central, right? It has two sp3 orbitals that are full. That's two lone pairs, and you see them in the Lewis structure right here and right here. It has two sp3 orbitals that are half full. These can form bonds, this one and this one. One of them is the sigma bond here, one of them is the sigma bond here. You see how that works out?
And so that's not the same thing as counting the valence electrons, or is that exactly what you're working with? The valence electrons?
Not, you mean like when we're doing the Lewis
yeah,
structure kind of thing? No, because we already have the Lewis structure here. We're
Okay.
starting from the Lewis structure. Notice though, that's a good point, right? You have to have the Lewis structure to be able to do any of this stuff, right? I've been giving it to you, but you guys know enough to be able to draw it yourself. So that canceling of the electrons where you subtract them, that's
Oh, it's
just
already
part of the
taken
procedure
care
for drawing the Lewis structure.
So once those bonds are formed, the filled sp3 orbitals just exist by themselves, or I don't understand with that picture. You said two of them,
Okay.
yeah.
Well, I don't want to erase that because we're continuing. So this is this oxygen right here, okay?
Yeah.
So the picture of that oxygen with the hybridized orbitals on it would be four equivalent sp3 orbitals, 3/4 p, 1/4 s. So each one of them might be something like that, right?
Yeah.
There's going to be four of those forming a tetrahedron. Okay. In two of those, doesn't matter which two, pick any two, you're going to have lone pairs of electrons.
Okay. So
The other two, 109.5 degrees from each other, are going to each form a sigma bond, one here and one here.
all right.
Is that kind of what you're asking?
Yeah, that's what I was asking. I just wanted to visualize it kind of.
Are you guys still following? See the picture? So let's see, let's continue with this thing. D. What kind of bond is it? It's a sigma bond, right? And which orbitals are overlapping to form this sigma bond?
sp2.
Carbon sp2. You have to specify which type of atom, right? Carbon sp2 with carbon what? sp3. Specify whatever. Can you guys read this notation back there? Is it big enough? And that's that one. E's, it's this bond right here. I think you guys are getting tired of it, just finish it out though. Tell me which orbitals overlap to form bond E between the carbon and the hydrogen here. It's a sigma, right? So carbon sp3 and hydrogen
1s.
1s, right?
Cool.
Does it matter which one you put first, like carbon?
It doesn't matter, no. Yeah. That's a good point. I meant to mention that. I forgot to. Did you guys all catch that? When you're writing it in this notation, I could have written carbon sp3 hydrogen 1s or hydrogen 1s carbon sp3. It doesn't matter. Either way is fine. Almost done. E, F. What kind of bond is F? Sigma. Which orbitals overlap?
SP3, carbon.
Carbon sp3 and bromine what? 4p. Good. 4p, right? Who said that? You're right. Not me. Both you said it together? Yeah. Anyway, whoever said it, good. It's not 2p because the electron configuration, the valence electron configuration for bromine is, well, it's argon, then it's 4s2, 4p, 5. Right? So yeah, it's bromine, 4p. On a multiple choice test, a wrong answer would be sigma, carbon sp3, bromine, 2p, or something like that. And notice, when we look at the valence electrons in bromine, okay, 4s2, 4p5, there are 1, 2, 3 sets of filled orbitals. There are 3 lone pairs on the bromine in the Lewis structure. These are the lone pairs. There's one bond. Comes from that orbital there. It works out. G. What kind of bond is it? Sigma. Which orbitals overlap?
Carbon S,
Carbon what?
SP3.
sp3 with
And it's nitrogen sp3.
nitrogen sp3. What's that? H and I are the same as each other, right? And they're both sigma bonds, right? And which orbitals overlap? What? Nitrogen sp3? Or the hydrogen 1s? Okay.
sp3.
Real quickly, the nitrogen, same idea. Valence electrons for nitrogen are 2s2, 2p3. One full valence orbital, one lone pair, 3 bonds, 3 half full valence orbitals. Actually, I didn't have it right. One lone pair, 3 hybrid orbitals that are half full. Yes.
On the H and I, does that say NSP or SP3?
sp3. Oh, that's a 3. It's just.
Okay, no, it's fine.
And that's that. That's hybridization theory. Any questions on that? Yeah. Yeah, you guys have molecular orbital theory and hybridization theory. So we can move on to chapter 10.
I think we should call it
By the way, if you happen to read the textbook, very last couple pages, they talk about benzene, C6H6, and they're, I'm not going to talk about it. What they're doing is they're mixing together hybridization theory and molecular orbital theory. I don't think there's much value in doing that at this point. So if you read it and it's confusing to you, that's probably why, because they're talking about 2 different theories together. So, something totally different. Chapter 10. Those of you that actually had Chem 142 or so, you've already had this stuff. Okay? These are types of chemical reactions, single displacement, double displacement, combination, decomposition, stuff like that, right? So I'm going to go through it fairly rapidly, but I'm still going to cover it because I'm getting the impression that some people haven't had 142. So it's still important stuff, right? It's just that you really should have seen this already.
All you do is have another double. Is that what you like?
That's it.
I can ask, when it's triple bonds, how would it look when it's triple bond? What's triple bond?
Yeah, so you're gonna have 2 pi bonds and 1 sigma bond.
I should have asked.
This is chapter 10.
So they're saying that really the triple bond instead of that will be carbon.
It would be, yeah, it would be 2 of those pi bonds.
Like another one?
Oh, you don't have to draw. It's just 1 bond.
How would you distinguish that from one pi, one bond, double bond and triple bond? You know what I'm asking?
Yeah, I know you're asking.
Should I have asked him?
Yeah, you might still.
Is it too late to ask a question about what you were showing us?
Sure.
So how do we distinguish when we're writing them down? Like pi, carbon 2p2 from a
That's sp2.
Oh, sorry, sp2 from a double bond and a triple bond, since they're both.
Well, okay, the question is, how do you know if a double bond or a triple bond, what do you write?
Yeah.
If it's a triple bond, that means, say for a carbon, it's going to be a sigma and 2 pi's, right? That's 6 valence electrons. There's only room for 1 more bond, which means there's only going to be 2 electron groups. So it's going to be sp, not sp2.
So the only thing that changes is that.
Yeah.
All right.
And so whenever there's a triple bond, that atom is going to have to be, that has a triple bond on it, it's going to have to be sp hybridized, in hybridization theory. So it always is. Double bonds are sp2.
Okay, thank you.
Yeah.
I'm so confused.
So an example, combination reaction. 2 species combine to form 1 species. For example, gallium combining with oxygen to make gallium oxide. Metal oxides, that is metal with oxygen. Some of those, when they combine with liquid water, form metal hydroxides. And metal hydroxides are soluble in water. So really, even though you write potassium hydroxide aqueous, what that means is it's potassium ions and hydroxide ions. So in general, one of the things that you should memorize is figure 10.8 on page 315. This gives you the metals, the common metals that will combine, the metal oxides rather, that will combine with water to make metal hydroxides. You guys find that figure? So lithium, sodium, potassium, rubidium, and cesium, and then calcium, strontium, and barium. Whenever any of those metal oxides, when they react with water, they produce the metal hydroxide. So for example, so this is one of those, that's potassium. So this is the metal oxide, potassium oxide, combining with water, making the metal hydroxide. How would I write that reaction for the metal oxide that forms from strontium? So first of all, what's the formula for the oxide that forms from strontium? See strontium right there? When I say oxide, that means, O with a -2 charge, right?
SR3O2, or no?
So yeah, what I'm asking is the formula for strontium oxide first. These are solids reacting with water. What's the product? In other words, that's one of those metal oxides, right? It's reacting with water. What's the metal hydroxide? SROH2. It's called strontium hydroxide, right? You see how that works? So knowing figure 10.8, you can predict several chemical reactions. When some non-metal hydroxides react with water, they form acids. So you can say this. So when these metal hydroxides in figure 10.8, metal oxides, combine with water, they make metal hydroxides, which end up being soluble. And when they dissolve in water, when they're soluble, means that they produce the hydroxide ion. And any solution, like the solutions that result from these, that contain hydroxide are said to be basic, as opposed to acidic. It's one of the definitions of a base, something that produces hydroxide ion in water. And these are still examples of combination reactions. Some non-metal oxides, when they combine with water, form acids. For example, sulfur dioxide. Can combine with water to form this stuff. What's the name of this stuff? You guys know? What's the last part of that? So I heard
Sulfurous acid.
Right? Yeah, that's right. So sulfuric says SO4, H2SO4. Sulfurous is H2SO3. Just a nomenclature review. Polyatomic ion is SO3, 2-, which is sulfite. ITE becomes LUS. ATE becomes IC. You guys remember that? Sulfurous acid. Anyway, this is an example of how some non-metal oxides can combine with water to form acids. So acids, aqueous acids, actually dissociate to produce hydrogen ion or hydronium ion. I'm not going to get into that difference, but basically means the same thing. And any solution that contains these is said to be acidic. So those are a couple of actually 3 different examples of combination reactions. That's probably a good place to stop for today.